Welcome to the lecture series. In this lecture, we are going to discuss about the compensators in the control system. So compensator is nothing but a device or circuit added to a control system to improve its performance such as stability, transient response and steady state error. So before getting into the lag compensator, we'll discuss the type of compensator which we have discussed under the compensators. So first circuit is a lag compensator. So here you can see a capacitor is added in the loaded side. So you can see a capacitor is connected in a series with the R2, that is it comes across the load side, so it adds a phase lag to the output. Where in the lead compensator you have discussed it earlier, there's a capacitor in the parallel to the R1 and it acts as a leading the phase angle. And last one is lag lead compensator. It acts as the both lag and lead compensator, where the capacitor is loaded in the parallel to the R1 and also loaded to series with the R2. So it gives the phase lag and phase lead. So these are the basic circuits, and in depth we are going to discuss about the lag compensator. So what is this lag compensator is? We have a phase lag, and this is an electrical circuit designed to produce a sinusoidal output with a phase lag, and this is the where the sine we have a higher frequency components reducing the steady state error, and it enhances the stability by decreasing the overshoot and increasing the phase margin, and by acting as a low pass filter it smoothens the out high frequency noise while maintaining a consistent steady state output. And let us discuss how this works. So first one we know that is the phase lag, right? So phase lag, the compensator adds a delay to the phase, that is delay to the phase in the output signal relative to the input, and that is why sometimes called as a lag network. And it acts as a low pass filtering also, and significantly reducing the amplitude of the high frequency signals. And next one is stability and steady state error. And steady state reduction, yes, it helps in reducing the steady state error of the control system, especially for the ramp inputs. And next is the performance enhancement, and thus it improves the performance and ensures the stability enhancement by increasing the phase margin, decreasing the overshoot, and it improves the overall stability of the system. And why we use, yes, we are this is the key points like increased stability, reduce the overshoot, improved steady state accuracy and noise filtration, as it acts as a low pass filter also. And key effects also includes the increase the rise time, enhances stability, and eliminates the high frequency noise. And circuit overview, as we know, R of S is nothing but the input and C of S is nothing but the output, and G of S acts as functional. The compensator is added in the feedback circuit, and thus taking upon the compensator action, the error detector rectifies the error and it regulates the control system. And next is the transfer function. You can see there is a capacitor value of 1 by SC here, and we know the transfer function is the relationship of the output to the input. So we are rewriting the V naught of S divided by V of S, that is 1 by alpha S plus 1 by T divided by S plus 1 by alpha into T. And we know this tau is nothing but R2C. So alpha is nothing but R1 plus R2 divided by R2. So we are rewriting these equations and we are applying it in the transfer function of the lag compensator. And frequency response and phase lag, yes, we know that the compensator exhibits higher gain at the lower frequency compared to the higher frequencies, and this property helps in improving the steady state accuracy without determinately affecting the system's transient response or the high frequency stability. And comparing to the lag or the lead compensators, the key difference is it produces a phase lag, but it produces phase lead. And phase lag there is lag compensator, it improves the steady state error, and the lead compensator improves the transient response. So it improves the steady state and lead improves the transient response. And if you use the lag lead compensator, it offers both the balanced approach. We can get the stabilized system behavior. And here you can see for a bordered plot we have the magnitude and the phase. And we know, we have discussed in the bordered plot, like we have two types of plot, that is magnitude plot and phase plot. Where this magnitude plot, it can be measured in the decibels, and phase plot will be measured in the degrees. And this is the sample thing for the transfer function which we have derived. So the minus 20 decibel is taken here for the frequency of particular omega m, and the graph is plotted along the frequency and the decibels. And design considerations, as these are the four things we have to consider. Pole and zero placement, we have to select the poles and zeros properly, and we have to set the low frequency impact, and we have to consider it. And gain adjustment, yes, the system gain has to be adjusted carefully to meet the steady state requirements. And last one is phase lag limit, we have to set the limit also, often less than the 2 degree, to maintain its stability. And practical applications, yes, we can use in the cruise control system, sensor feedbacks and motor speed regulations, and unlock and digital control. When the cruise control on everything, we can see it is mainly focusing on the steady state error to maintain its stability. So wherever you have some speed regulations or acceleration part or control automation side, you can utilize this. And summary and key takeaway, you can see here have discussed about the fundamental key concepts, and we have discussed the transfer function, that is mathematical representation. So design techniques, like what are the considerations you have to take, and we have also discussed the practical applications. So depending upon this, we can use this lag compensator for a suitable applications. Thank you.